Hello everyone, welcome back to Labtube. In this video, I will continue doing a question that I did in another video. It was question 17 from section 16.7. The question was to evaluate the surface integral x squared z plus y squared z when S is upper hemisphere of radius 2 centered at origin. So last time I mentioned that we have to do two steps. One, parameterize, then apply these three changes. Change the boundaries to boundaries of the new variables or new parameters. Change variables of function to new variables, and then change ds, which is integral element, to this guy, which is integral element for u and v. And in the previous video, I showed how to parameterize hemisphere using spherical coordinate. I just used theta and phi. In this video, I'm going to repeat this question, but this time, parameterization, I will use another parameterization. And note that the result should be the same thing because surface integral is independent of the parameterization. Okay, what is the parameterization I'm going to use for hemisphere this time? So, I have x squared plus y squared plus z squared equals to 4. This is an equation which gives us the sphere of radius 2. Now I can cook up a function out of this whose graph gives us the sphere, at least part of the sphere. So what is that? I can take everything to the right hand side but z. So I have z squared 4 minus x squared minus y squared. And then I can find square root. But note that when I'm taking a square root, I cannot put either plus or minus. If I put plus, I will get upper hemisphere. If I put minus, I'll get lower hemisphere. Here, since I have z positive, I will stick with the positive one. Okay, so that's the graph. So note that f of x, y, the graph of the function f of x, y equals to 4 minus x squared minus, this is minus, yes, this is minus y squared so if I want to get the whole hemisphere, I have to consider the image of this upper hemisphere on xy plane. On the region D is given by x and y such that x squared plus y squared is less than or equal to. It is a disk of radius. It is a disk of radius 2 centered at origin. Okay. So this is very general thing. If you have a graph of a function, you have a nice parameterization for that. And that parameterization is given by, to parameterize a surface, I need two parameters. If the surface happens to be graph of a function, those two parameters are x and y. And the graph, the vector function which gives you that surface, x is equal to x, y is equal to y, and z is equal to f of x, y. So in our case, x, y, 4 minus x squared minus y squared is the parameterization. Okay, then again you can find our x, our y, and do all those steps. But in this specific case, actually we know what is our x cross our y. This is now a good time to do practice stop video and try to find our x, our y, cross them. But at the end, what you're going to get is equal to minus fx minus fy and y. And then the length of that is going to be 1 plus fx squared, fx squared plus fy squared plus 1. Okay, let's then in this specific case, when the surface is the graph of a function, everything is ready to use. So our x cross our y, you just need to use this formula. Find partial derivative of f, which is here, with respect to x. So it is going to be minus 2x over 2 root 4 minus x squared minus y squared. Note that I'm using this fact, this differentiation fact, that if you have square root of box and you want to find its derivative, it is going to be box prime over 2 root box. That's the differentiation rule. If you know that, that's the step. So that's fx, square that, plus fy, which is minus 2y over 2 4 minus x squared minus y squared, then square it plus 1. Okay, then I can cancel these guys here, 2's, they cancel out, and then find common denominator. The denominator, square them, first thing is x squared, then plus y squared, and this guy is going to be 4 minus x squared minus y squared. And there is 1 also here, so if I put this as the denominator of 1, then I'm going to have 4 minus x squared minus y squared there also. Okay, you can simplify this because this cancels that, this cancels that, and the result, now I can write it here. The result is 4 is in the numerator, so square root of 4 is 2 over 4 minus x squared minus y squared. Okay, so we have this parameterization coming from the fact that it is, the upper hemisphere is the graph of a function, and we use these facts, these given facts, that our x, our y cross is given by that, and its length is equal to square root of fx squared plus fy squared plus 1. And then we continued, and then we found this. So then I don't need any other thing here, so I can erase. What I need to keep is first the parameterization. Parameterization of the graph of a function is always like this. X is x, y is y, and then you have f of. This is one very nice parameterization for the graph of a function. And then we found that our x cross our y is equal to 2 over 4 minus x squared minus y squared. Okay, and something else that we know that the region we are working is the disk of radius 2, centered at origin. Okay, so these are the facts. Now I can erase all these things. Okay, and now I can write my surface integral and try to apply all those changes. First thing is to write down the boundaries for x, y, z. Let's just put d here for now, for that step. And then, so x squared. So I have to plug in x for x, y for y, and root of 4 minus x squared minus y squared for z. So I'm going to get x squared times, I can factor out z. So I have x squared plus y squared, 4 minus x squared minus y squared. That's the z. So this is my integrand. I plugged in my variables into my integrand. And then ds is length of this, which I already found, and it is 2 over minus 5 dx dy. Okay, for now I can cancel these two, and I can rewrite this d2 times x squared plus y squared dx dy. Now I have a double integral. It is not iterated integral yet. I have to change this to iterated integral. But since my region is circular, it's a disk, yes, the best thing to do is to change my variable from Cartesian to polar coordinates. So I have disk of radius 2 gives me, okay, this is the changes I need to apply. Disk of radius 2 centered at origin in polar coordinates given by this r going from 0 to 2, theta goes from 0 to 2 pi. So now I can do r theta x squared plus y squared. You plug in r cosine theta in x, r sine theta in y, square them, you get r squared. So you get r squared here. For dx dy, you have to recall in polar coordinates, dx dy is equal to r dr d theta. Okay, now I have an iterated integral. I have 2 here, r to the power 3, antiderivative of r to the power 3 is r to the power 4 over 4, 2 is outside, 0 to 2 pi, go from 0 to 2 d theta. And then you plug in 2 here, I get 16 over 4 is 4, so 2 times 4, and that's 0 to 2 pi, minus 0 d theta. And then integrate this, so it is 8 theta, go from 0 to 2 pi. It is 16 pi. Okay. Very quick wrap up. I need to first parameterize, then use this 3-step change and change it to double integral or iterated integral. This time I use the fact that the upper hemisphere is graph of a function. What is that function? That function I found using that equation. And then I have this parameterization, which you can always write for the graph of a function. For x, you plug in x, for y, plug in y, and for z, you plug in the function itself. And in that specific case, it is given, so you can check your book, or you can compute Rx cross Ry with this specific parameterization. The length is given by square root of fx squared plus fy squared plus 1. And we computed that. And then we applied all the changes. What we got was a double integral, and the region over which we were integrating was circular, or disk, yes? Then we know from previous sections that if you have such double integral, it is better to change it to polar coordinate. In polar coordinate, you have to apply all those changes. What is the region? What is your function in polar coordinate? And what is dx dy in polar coordinate, which is equal to r dr d theta. Then I have an iterated integral, evaluate inner one, evaluate outer one. The result is 16 pi. Note that the value that we got from the other parameterization was exactly the same value, 16 pi. And this is a general fact. It doesn't matter what parameterization you take. You have to just pick a parameterization for surface integral. We choose that, you do apply all those steps, and you will get value for your surface integral. Thank you for watching this video.